So now we know what eigenvalues and eigenvectors are. They're these special numbers and special vectors such that if I take my matrix A times my eigenvector x, I get a vector in the same direction as x, but scaled by a factor of lambda, my eigenvalue. Okay, we know what they are, and we know how to find them. It turns out, as in most things in math, that's much easier in Matlab. Okay, so in Matlab, this is really, really easy to find these eigenvalues and eigenvectors. I just type in this command, t comma d equals eig of A, semicolon. Okay, and what this does is it gives me two matrices, T and D, and the columns of T are my eigenvectors. So columns of T are eigenvectors, evex, and D is a diagonal matrix. Okay, it's only got entries on the diagonal, zeros everywhere else. So D is diagonal with lambdas on the diagonal. Okay, so this is what I get. I basically get this big T matrix, T, which is x corresponding to my first eigenvalue, x corresponding to my second eigenvalue, and so on. So x corresponding to my nth eigenvalue if I have an n by n A matrix. Remember, if I have an n by n A matrix, then I'll get exactly n eigenvectors and n eigenvalues. Okay, and D, this D matrix that I get out, is equal to a purely diagonal matrix of lambda 1, lambda 2, dot, 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 all the way down to lambda n, zeros everywhere else. Okay, and this is kind of nice. So what we have here is all of the eigenvectors as columns of this matrix T, all of the eigenvalues as diagonal elements of this matrix D, and x, the first column of T, is the eigenvector corresponding to this eigenvalue lambda. The second column is the second eigenvector corresponding to this eigenvalue, and so on and so forth. So they're arranged in the correct order. And this is really nice. So Matlab just gives you the eigenvalues and eigenvectors of a generic matrix A using this simple one-line command in Matlab. Really, really nice, really, really simple. Okay? Now, what's interesting is that once you have these eigenvector and eigenvalue matrices from Matlab, or you could do this by hand if you want to, we also have this interesting property that if I take D, this diagonal matrix, D to the power, let's say capital N, D to the power N, if I take any diagonal matrix and I multiply it by itself, all that happens is that the diagonal elements get multiplied by themselves. Okay, so if I take this matrix times itself, I get lambda 1 squared, lambda 2 squared, dot, 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 lambda n squared, and zeros everywhere else. Try this out. Try this out for a simple system like 2, 0, 0, 3. And if I multiply it by itself, if I square it, then you get 2 times 2 is 4. And then 0 times 2, 3 times 0. The off-diagonal elements are both 0. And then the last one is going to be 0, 0 plus 3 times 3 is 9. And you end up getting the diagonal matrix with the diagonal elements squared. Okay? So if I take d to the power n, I'm going to get the same diagonal elements, lambda 1, but now to the power n. Lambda 2 to the power n, dot, 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 lambda, my last eigenvalue to the power n, and zeros everywhere else. Okay, this is kind of cool. It's not just cool, it's also incredibly useful, okay? Because it turns out that there's this very important property of a matrix A and its eigenvalues and eigenvectors T and D. Remember, I wrote AX equals lambda x. And so I could say A times T is the same as A times x lambda 1, and then a times x lambda 2, and then a times x lambda n, and dot, dot, dot. And so I could say a times t, this matrix of eigenvectors, is the same as t times d. Okay, if I take t times d, then what I get is a new matrix out where I still have all of these directions, but they're each scaled by lambda 1, lambda 2, and so on and so forth. Okay, so this is the matrix form of the E-vec relationship. That's what this is, the matrix form of the eigenvector relationship. And so what I can do is I can say, well, I can solve for A, or I can solve for D by taking the inverse of this eigenvector matrix T. Okay, so we're going to do that. Why would I want to solve for A in this way? Well, we're going to find that, for example, if I take A to a power, then writing it in the following way is going to be really useful. So we can solve for A. And we solve for A in the following way. We say A equals T times D, and then I multiply both of these by the inverse of T. Okay, so T times inverse T is the identity. And I get A equals T, D, T inverse. Matrix T times matrix D times matrix T inverse. This is what A equals, okay? Now, if I have a full set of eigenvectors for my square matrix A, then I'll be able to write this. This is fine. Sometimes you can't do this, but most of the time you can for most matrices A. And so if I want to take my matrix A to the power n, I can take this expression and multiply it by itself n times. So this is really like T, D, T inverse to the power n. Okay? And that's really like T, D, T inverse times T, D, T inverse times dot, dot, dot times some more T, D, T inverses, where I have n of these terms. Now this is the really, really cool part. This is why we want to write A this way, because this is actually much, much simplified. Okay, all of these T inverse T's in the middle cancel out to identities. So what I really have is T times D. These cancel, I get another D, times D. These T's cancel, I get another D, dot, 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 D. And finally, I get a T inverse on the right-hand side that doesn't cancel. So after all this is said and done, I get T times D to the power n times T inverse. Now, this might not seem a lot simpler than writing A to the power n, but remember, if I have a big, nasty, generic A matrix, then multiplying it by itself a lot of times might be really expensive, and it also might be complicated. But here, the only term that I'm multiplying a bunch of times is this diagonal matrix D. And taking D to the power n is super simple. I just take each of its elements and take those to the power n. Okay, so D to the n is really easy to compute. And so this is a simplified expression. Okay, good. Now, the last thing that I want to tell you is why this would be interesting to look at A to the power n. So at the very, very beginning of this lecture, I told you that there might be some connection to when matrix systems of equations blow up without apparent explanation. And I think that now we're ready to make this final connection. Okay? Okay, so I told you that we have this system x at time k plus 1 equals a times x at time k. And the index k might represent, which day of the iteration. So we have xk plus 1 equals a times xk. This is, remember we did the weather modeling or the disease modeling where x was the state of whether or not you were sick, healthy, or in recovery. In the infectious disease case, or in the weather case, it was sunny, cloudy, or rainy. And this matrix A tells me what my probability of those states are at some future time x. So if I start off on day 0 with some state, then on day 1, I can get day 1 by just taking A, multiplying by A, right? So x1, my state on day 1, is A times x0. Now, if I want to go to state on day 2, I multiply by A again. That's equal to A squared times x0. And so on and so forth. So if I do this n times, then x on the nth day is given by A to the power n times the probability on my first day. Okay, good. So if this sequence, sometimes this sequence blows up to infinity, sometimes it converges and decays to 0, and we're going to explain why that happens based on these eigenvalues and eigenvectors of this matrix A. Okay, so that's what we'll do in the next segment.